Last time on Deep Sky Detail, having an exposure length that overcomes the read noise is much better than shorter subs. But are 10-minute subs better than 2-minute ones, even if the 2-minute ones have sufficiently overcome the read noise? That was a good video. We should follow it up. What did you say? Oh, I was just saying that we need to look at long versus normal exposures. Probably 10-minute versus 5-minute subs. I agree. I wonder what the results would look like. Well, let me check. We'll use the patent-pending Time Machine Preview DSD viewer. We've only got a few seconds.
Holy cow. I wasn't expecting the results to be this clear. This is really interesting. So basically the 300-second subs.
Rats. Lost the connection. Welcome to Deep Sky Detail. I've done 2 experiments testing how much better 10-minute subs are than 5-minute subs. But first, a few months back, I did an experiment where I tested whether 2-minute subframes are better than 15-second subframes. If you're new to astrophotography, then let me give a bit of the background. In astrophotography, the things we're imaging are really, really faint. Well, except for the stars. Ideally, we should just be able to take a really long exposure to bring out the detail, but it's hard to track an object as the Earth rotates as they move across the sky. So we put our telescopes on mounts that track the stars. Too long of an exposure can be bad because the gears in the mount aren't perfect, and you get errors in guiding. The stars also start to get saturated. Plus, there might be light pollution that can wash out a long exposure. So instead of one long exposure, we take several shorter exposures called subframes or subs and average them together. We call this averaging stacking. With a perfect camera and perfect conditions, the average of the shorter subframe should be pretty much identical to one longer subframe. But cameras aren't perfect and conditions aren't perfect. So the question is, what is the ideal sub-exposure time? Should you go as long as you can, or should you keep them shorter? And that's what my previous video on the subject was about, comparing very short 15-second subframes to more normal 120-second subframe. The answer in terms of signal-to-noise ratio is clear. The 120-second subframes were much better. Signal-to-noise ratio, or SNR, to put simply, is an important factor for bringing out detail in your image. The more SNR, the better. A stack of 160 15-second subframes, which is 40 minutes of total exposure time, only had half the SNR as a stack of 20 120-second subframes, which is also 40 minutes of total exposure time. So the longer exposures were better. I ended that video with a question: what about 10-minute subs? So this video will be comparing 5-minute subs with 10-minute subs. I'll be checking SNR, tracking star size, and trying to assess something called blotchiness or modeling. So what equipment will I be using? I've got a 6-inch Ritchie Creation at a focal length of 1,370 millimeters. Attached is my ZWO294 MM Pro camera on an Orion Sirius mount. I'll be using an off-axis guider. The experiment took place in Bortle 6 or 7 sky, meaning there was a good amount of light pollution, but it could be worse. My first target is Messier 101, and the second target is the Iris Nebula. I systematically alternated between 10 and 5-minute subs each night of imaging. This should help rule out systematic differences between the subframes that aren't due to the actual length of the subframe. In other words, it helps eliminate third variables like weather on the subframe. The first experiment with Messier 101 will only examine the SNR of 2 types of subframe. This experiment is kind of like a pilot study to see if my mount can actually handle 10-minute subs. It would also help remove some doubt that some of you may be having about SNR as a measurement. SNR can be a really good measurement if done correctly. It can be a bad measurement if the wrong assumptions are made. I did a video on it. If the pilot N101 test agrees with the larger Iris Nebula test, then hopefully you can have more confidence in the result. In the second experiment, I'll be looking at the Iris Nebula. I'll first look at signal-to-noise ratio of the bright area compared to the darker areas. More on that in a minute. I'll also examine the size of the stars, tracking, and explore blockiness or blotchiness. Let's talk about the debate for a bit related to SNR. Does sub-exposure length matter? In my personal view, too short of an exposure can be bad for SNR. But after you reach a certain point, it doesn't matter. But a while ago, I saw a presentation by Tim Hutchinson on the Astro Imaging channel where he said this.
The real question is, how long can I go? Because remember, the longer we expose, the greater impact we have on our shot noise for every single frame. And then as we stack those frames, the better we're going to be when we're trying to drive that noise down away from the signal that we've captured.
He then said,
as I said already, your camera doesn't have infinite dynamic range. So if you have a little teeny tiny signal like this that you try and stretch, what's it going to look like? Well, you've taken that little teeny tiny signal of a couple of ADUs and stretched it over a whole bunch of ADUs. It's going to look blotchy. That's where you get this mottled kind of blocky look that you see in some images.
When I first heard this, I was kind of skeptical, to be honest. The traditional view that I've held is that as long as the signal overcomes the read noise, then very long subs are pointless, especially if you have any kind of light pollution. If the signal hitting one pixel is something like 100 photons per 120 seconds, and for another pixel it's 110 photons per 120 seconds, the average of a whole bunch of subframes is going to be about 100 for the first pixel and 110 for the second pixel. If you have a 600 second sub, then the first pixel will average out to be 500 photons, and the second will average out to be 550, as long as the signal overcomes the read noise. Stretching is done in software, so everything should be good. But as time went along, I had to ask myself, could I be wrong? So I tried to figure out how I could be wrong. One way I could be wrong is maybe the fainter parts of the nebula would benefit from longer exposures. Because they are so faint, the signal might be near the read noise. If this is true, then if I do an SNR measurement, a long 10-minute sub should get more SNR for the faint details compared to the 5-minute sub. But the SNR should be similar for the medium bright and brightest areas. If I graphed it, it might look like this, or this, or this. I do doubt this though. I think that light pollution will destroy a lot of the faint signal, meaning that there will be too much light pollution noise in the fainter areas for it to make a difference. If that's the case, then the graph would look like this, or this, or this. Notice that the difference in the two hypotheses depends on the SNR of the faint areas. If I'm right, there will be no difference. If longer subs do matter, there will be a difference in the fainter areas. SNR is the measurement of choice here. Another way I could be wrong is related to what Tim said about amplifying faint signal. Now, Tim is an electrical engineer by training, so he probably knows a bit more than me about converting analog signal into a digital output. How that conversion would lead to blockiness is a bit beyond my comprehension, but I started thinking about faint signal, where blockiness can and does show up in a lot of astrophotos I've taken. And I thought, well, if the signal is very faint, then the range of values the sensor can detect is actually kind of narrow. If there are 5 photons hitting the sensor per subframe, on average, 99% of the subframes, your sensor will detect between 0 and 12 photons. But if you expose for 10 times longer, on average, the sensor will detect 50 photons. But the range of probable values will be from 33 to 69. The range of probable values is 3 times greater with the longer exposures. It really seems like you have a bigger range to work with if you expose longer. This could allow you for more incremental brightness values when you stretch your image. So exposing for longer may actually decrease the blockiness of the image for the fainter areas. I don't know if this is correct, so in my test, I'll check the number of unique brightness values in a stack.
So I imaged about 1 hour of Messier 101. Guiding for the 300-second subs and 600-second subs was actually really good. I threw out an equal amount of time for both types of subs due to guiding errors. 1 600-second subframe and 2 300-second subframes. Not bad. I will say that the night's eye image were pretty clear. There was no wind and I had good polar alignment, so I wouldn't always expect 600 subframes to perform as well as 300-second subframes, especially if there's a lot of wind or your mount can't handle it. I think I was lucky more than anything else. I also threw away 1 more 600-second sub and 2 300-second subs because of high-level clouds messing things up. Also not bad, and also I think I got pretty lucky. Both sets of images were calibrated with the darks flats and dark flats, although I had some pretty bad dust motes, but I'm not here to make a pretty picture. Let's first analyze some star shapes. Okay, so I'm going to do the analysis of the stars first for the Iris Nebula. And I've got the 300-second sub stack on the left, and this the stack of 600-second subs on the right. And I've selected the same area, and I've just run a dynamic PSF in serial with the same settings. And for the 300-second subs, we had 44 stars total, and the average full width half maximum is about 5.5. You can see that in the X direction is 5.75 and the Y direction is 5.04. In the 600-second subs, we also have 404 stars, with the full width half maximum also being somewhere around 5.5. In the X direction is 5.72. In the Y direction, it's 5.04 or 5.02, or the star sizes are pretty similar, meaning that both of these images are kind of equally blurry. To test SNR, I took the core of M101 and divided it up into 121 equal sections or samples. Each of the two stacks were aligned in serial. I then took a subframe, got its SNR for the 121 samples, then stacked an image, got the new SNR, and kept repeating for all the subframes. I then repeated it for all the exposure lengths. You know, it took a lot of work. You might consider subscribing if you haven't yet. I'd appreciate it. All right, so I've got all of the data extracted for the different parts of the galaxy for M101. And we're gonna go and see if the SNR is different between the 300-second subs and the 600-second sub. I'm gonna go ahead and run this analysis. Holy cow, I wasn't expecting the results to be this clear. This is really interesting. So basically the 300-second subs got more SNR than the 600-second subs, but the result wasn't really what we call statistically significant. So there's probably nothing going on here.
Okay, this analysis is a bit more complicated. For each type of subframe, I had a little over 3 hours of data. There were some guiding errors. For the 600-second subs, I threw out 2 frames. For the 300-second subs, I threw out 4 frames. So in terms of integration time lost, it was again equal. Can't believe my luck. I was also really careful with polar alignment though, so maybe it wasn't 100% luck. The nights were generally clear that I imaged on, and so I threw out 1 600-second sub and 2 300-second subs due to the roof of my house interfering with the images. This time I took 676 samples. You'll see why in a few minutes. But really, I needed more samples this time. Each of the 2 stacks were aligned in serial. I then took a subframe for one of the exposure types, got its SNR for the 676 samples, then stacked an image, got the new SNR, and I repeated it for the subs on the other exposure length. You know, this took a lot of work. You might consider subscribing if you haven't already. I'd appreciate it. But that's not all. Then I divided the samples into 3 groups: bright groups, medium brightness groups, and dim groups. Bright groups were the brightest 25% of samples. Dim groups were the bottom 25%. Mid was the middle 50%. Let's see what's going on. Let me run the analysis. Before we look at the SNR results, let's look at the blockiness question. I've run the data for the SNR results, and I'm pretty confident in those results. Like, really confident. It's the blockiness question that troubles me. And I think I need your help to figure this out. First, I'm not sure whether I've got a good analysis for it. And second, whatever analysis I did come up with might be explained better by something else like shot noise. If you have a better way of doing things, let me know in the comments. I'd appreciate it. So for the blockiness question, I figured I could just determine the number of unique ADU values for each stack. ADU translates to how bright a pixel is. How many bits an image determines how many unique ADU values an image can have. So a 16-bit stacked image can have 65,536 unique shades of gray. In a 16-bit stack, there might not be any room for decimal places, especially for the fainter parts of the target that you're imaging. The part of the image that I'm testing of the Iris Nebula has 11,694,368 total pixels. If I'm processing a 16-bit image, then there are only 65,000 total brightness values any one pixel can take. I'll talk about 32-bit stacks in a second, but that means some pixels have to have the same brightness value. For the 10-minute subs, the range of probable values might increase by about 1.4 due to increased variability of the shot noise. That might, in theory, increase the effective dynamic range. I put in theory in quotes and effective dynamic range in quotes here because I'm not confident these are the correct terms. This analysis, I think, has a lot of moving parts. More on that in a moment. So I stacked both 600-second subs and 300-second subs as 16-bit images first. The 300-second subs had 5,842 unique brightness values. The 600-second subs had 8,432 unique brightness values. That's 1.44 times more unique brightness values than the 300-second subs, right in line with a theoretical value of 1.41. So longer subs are better? Well, for a 32-bit image, we would have about 4 billion possible values. Now, when we stack an image, we don't have to worry about rounding error as much because we don't lose as much information. Let me show you what I mean. Let's talk about why you might expect to see more unique ADU values when you take longer subs for 16-bit images. So let's pretend that we have 2 pixels on our camera, and they're both recording different parts of the sky right next to each other. And we have 300-second subs and 600-second subs. Now, pixel 1, it records these values on 10 different subframes, and it has an average of 5.5 photons that it records over those 10 subframes. Pixel 2 records about 6 on average. So there's like half a photon's worth of difference. When you're stacking into a 16-bit image, and there's not enough room for rounding. What do I mean by that? Well, the stars in the image are very bright, so they're all going to be around 60,000, 65,000 ADU. When you stack those images, those stars get averaged as being bright. You only have a limited number of ADU values for the low signal areas. And so the stacking software knows this, and it says, well, we have to round these numbers both to 6, essentially losing some information due to rounding error. If you take 600-second exposures instead, you might get these values. Instead of an average of 5.5, you get an average of 11. Pixel 2, instead of an average of 6, you get an average of 12. And stacking software says, okay, those are actually different values. We can assign 11 for this pixel and 12 for this pixel. We have more room in the midtones than we do just in the faintest areas. And so we can assign different ADUs to the longer subframe. Now, the thing about a 32-bit image is that instead of just 65,000 unique values, you now have like 4 billion. You don't have to round anymore. There's enough space in the lower areas to where you can actually have this relationship. You have 5.5 ADU for one pixel and 6 ADU for another pixel, and it's fine. And so you still have 2 unique values, 32-bit stack of 300-second subs, and you still have 2 values for the 32-bit 600-second stack of subs. With the 32-bit, when you stack in 32 bits, you're not losing that information to rounding error, or at least not as much. So with a 16-bit image, the 600-second stack did have more unique brightness values. It seems like we're running into the rounding error problem. But what if we take our subframes and stack 32-bit image? Let's look at the number of unique values of each stack now. The stack of 300-second subs had 678,731 unique shades of gray. The 600-second subs saw only a 0.06 improvement with 679,118 unique values. So the difference is actually quite small. And I would say there would be no discernible difference when you process the image. I would probably say the same is true for the 16-bit images. 5,000 unique values with the 300-second stack may be enough to get a smooth image, but what do you think? In general, do you think looking at the unique values is a good way to go about this? I'm not really sure, but I think that if you do stack your images and you're worried about losing information if your subs aren't long enough, then I would stack a 32-bit image. Of course, there are a lot of other variables to think about, like the bit depth of your monitor, principles of human perception, the fact that unique values may just be part of the shot noise, or other things. Feel free to suggest another way of analyzing blockiness. So let's take a look at the SNR measurements of the Iris Nebula again. The SNR of both stacks was around 10 as an average of all of the samples. The difference was not statistically different, just like Messier 101 experiment. Also recall that in this experiment, we're going to be looking at the dimmest 25% samples, compared to the brightest 25. Let's go ahead and run that analysis. Well, it looks like for the 25% dimmest samples, there was no difference in SNR between the 300-second and 600-second stack. The 300-second subs and 600-second subs dimmest parts got about 4 SNR. The Bayesian statistics really favors the idea that there is no difference. Quick side note, if you're a stats geek, with traditional statistics, you can only reject the null hypothesis and can't really provide support for it. But with Bayesian statistics, it does give you estimates for how much the null hypothesis is favored. In this case, the stats say that SNR really is the same for the dimmest region. But what about even fainter parts? Could I have biased the analysis by only looking at the 25% dimmest samples? Maybe we won't see an effect because those dim parts are still too bright. Well, let's compare the dimmest 10% to the brightest 10%. The brightest parts got about 15 to 16 SNR, no difference there. But for the dimmest part, there was also no difference. Both types of samples were around 2.3 SNR. The 300-second subs dimmest samples had 2.3 SNR, and the 600-second subs also had 2.3 SNR. Okay, but what if the dimmest 10% of samples was also too bright? Let's do this again, but look at the dimmest 5% compared to the brightest 5%. Note, I'm only doing this analysis multiple times because I'm trying to disprove myself. My initial hypothesis was that sublength doesn't matter as long as you've overcome the read noise. Tim's hypothesis was that it does matter. I want to give Tim's hypothesis as much of a chance of succeeding as possible. So, when comparing the dimmest 5% samples, the SNR was 1.7 for the 300-second subs and 1.7 for the 600-second subs. We're running out of samples to compare. And any dimmer, we're getting into territory where the signal is just not discernible anymore from the light pollution in my area. It would take hundreds of hours to bring out any real detail for those areas. If I were in darker skies, then it might only take 10 hours. But that's why light pollution sucks. So let's recap. But before I do, these analyses took a lot of time and effort. I'd like to continue these type of videos. Please consider supporting me on buymeacoffee.com/deepskydetail or becoming a channel member. Memberships start at only a couple of dollars a month. I'm hoping to create an identical dual rig setup to make experiments like these a lot easier. To recap, this experiment was done with broadband filters in a moderately light polluted area. Because of this, the results should only be applied to broadband imaging in moderately or heavy light polluted areas. If you have the right conditions, a good enough mount, and a good polar alignment and guiding, long subs can be fine. You won't have to worry as much about computer storage, but star shapes can be similar, but you have to worry more about planes, satellites, high-level clouds, and other things on each subframe. In terms of signal-to-noise ratio, there's no benefit of longer subframes as long as you're above the read noise. Shorter subframes are fine, but not too short. Well, what about blockiness? Well, this one is tricky. I would say that it's possible shorter subs could lead to more blocky faint details, but I think you can mitigate this by just stacking in a 32-bit images. Even if you're imaging at 14-bit or 16-bit subframes, you can still stack 32-bit to retain all that information to get more precision in your averages. Analyses were done under light pollution. Why is that important? Well, light pollution destroys faint signal, so the really interesting faint wispy stuff that is truly close to the read noise of the camera gets eliminated. Because of this, these results only apply to broadband imaging in light polluted skies. So what about darker skies? I think there is an extremely credible argument for going as long as you can, like Tim Hutchinson claims. It's too bad I'm in light polluted skies. It would be nice to have some sort of filter that could mimic dark skies, wouldn't it? Something that could get rid of like 90% of the light pollution. It seems like a narrowband analysis might be the next step, comparing long and short exposures. If you enjoyed this video, consider watching this one on why light pollution sucks, or this one that the algorithm recommends. Thanks for watching.